In this video, we're going to focus on actually solving these linear first order differential equations. So we previously looked at a theorem that once the conditions in that theorem are met, we're guaranteed that the differential equation will have a unique solution. So now our goal is to find that solution. But in order to truly understand the method of solution that we're going to present, it requires a really good, if not a very good, understanding of the product rule from your first semester of calculus. So let's actually just do a couple, maybe consider it like a little game where instead of me giving you a function that requires you to use the product rule in order to find the derivative, what if I gave you the derivative and we had to try to figure out what the product was whose derivative would be that given function, right? So essentially, can we work backwards just by looking? So suppose the question is this, right? So the derivative of what would give me 2x sine of x plus x squared cosine of x. Now remember, the pattern in or maybe not the pattern, but the rule or product rule states, and there are several ways you could say it, but you could think of this as your f prime, and then this would be your f, and then that would make this your g, and then we can see that this is your g prime, right? So we can see the product would have to be x squared times the sine of x. So if we kind of work backwards, we could say, well, yeah, the derivative of x squared times the sine of x is what I have here, right? So the ability to work backwards is going to be key, right? Let's try another one. So let's say we had something like this. The derivative of what is equal to e to the x natural log of x plus e to the x times 1 over x. Well, I think we can clearly see the pattern here as well, because we know that so for instance, the derivative of e is still e, right? So that could be my f, that could be my f prime, and then we know that the derivative of the natural log is 1 over x. So this could be my g, and then this could be my g prime. And therefore the product is e to the x times the natural log of x. So the function whose derivative I have here is e to the x times the natural log of x, right? And it's actually a really good exercise, I think, to see if you can work backwards. Really, really helpful. Now let's try another one. I have a few more of these just to get the product rule juices flowing. Now suppose I have 4 times the square root of x plus 5 plus, and then I have 2x over the square root of x plus 5, right? So this one might be a little harder because I don't really see that clear pattern. But one thing we can do, we can sort of modify this second term, this fraction. And what I'm going to do is multiply the top and the bottom by 2. So I have 4 root x plus 5 plus 4x over 2 root x plus 5. Now, let me write this one other form. So 4 root x plus 5 plus 4x times 1 over 2 root x plus 5, right? So this is just a slight modification of the original sum that I have here. But now I think we can clearly see that if I say this is my f prime, then this would have to be f. And then thinking about what happens when you differentiate a square root, right? We see that pattern here. So this would be my g, and then this would be g prime. So I could say the derivative of my f, which is 4x, times my g, which is the square root of x plus 5, that will give me this, right? So this one was a little bit trickier, but again, thinking about the pattern, what we know for like linear functions and square root functions, we could modify this slightly so that it matches up perfectly with the result for the product rule, right? Now that's what it looks like when you have just one variable, like everything is in terms of x. But what if we up the ante just a little bit and say we're looking for a product that when I differentiate that product, I will get 8x times y plus dy dx times a quantity 4x squared plus 1, right? So now I have both x's and y's on this side, right? Well, let's see. If I call this my f prime, then I can see where this would be f, right? And then here, if I let my y be g, then I can see, well, the derivative of y would be dy dx, so this would be g prime. So therefore, the product, right, the product whose derivative is given on the right is this function. I don't know what y is, right, but I know I can see the relationship between y and dy dx. That's through the derivative. And then my f would be the quantity 4x squared plus 1, and then times y, right? Let's try one more. This is our last one, right? I know this is a lot of fun, but the idea is if you think this is fun, then you will like the process for solving these linear differential equations, right? So again, let's see if we can work backwards. And here we have 2e to the 2x times y plus e to the 2x times dy dx. So I think this one is pretty straightforward. I mean, we can see that because we know the derivative of e to the 2x is 2e to the 2x. So right away I can make that my f prime, and then this would be my f. And then that means this would be my g, and there you go. Its derivative is right here, so that's g prime. So the whole idea now is that the product, right? The product that when I differentiate it will give me this expression on the right is my e to the 2x times y. And the ability to work backwards like this is key in solving a differential equation. In fact, let me show you using this very last example of how this process is helpful. So let's say we had you were given this differential equation. So let's say you had this. I'm going to write this down. The 2e to the 2x times y plus e to the 2x times dy dx. And let's say I put some other function over here now, like x minus the sine of x. So suppose this differential equation was given to you and we were asked to solve for y. Right? So to solve for y, what we would like to do is, you see, the fact that you have a y here and a dy dx here kind of in separate terms, that makes it difficult. But because of the pattern that we see here, in that this right-hand side can be written as the derivative of this product, well, let's do that. let's write the left-hand side. Did I say right-hand side? If I did, I'm sorry. Let's take the left-hand side and write this as the derivative of e to the 2x times y, and then just bring down what's on the right, because I'm not changing anything on this side of the equation. I'm just rewriting this, recognizing that pattern as far as reversing the product rule. We have this. And you see the benefit now is I only have a y here, right? Because I've written this sum as the derivative of a product, and there's only one factor here that involves y. So if I want to isolate the y, let's think how we would do that. Well, first I would have to get rid of this derivative. But I know how to get rid of a derivative. It's an antiderivative. So I'd have to take the antiderivative of both sides with respect to x. So it looks like this. Right? So now I've gotten rid of the derivative on this side, and then it's really easy for me to isolate y. So before I go ahead and divide by the e to the 2x, let's go ahead and evaluate this antiderivative. So we have e to the 2x times y, and then antiderivative of x is 1/2 x squared. Antiderivative of minus sine x is a positive cosine x, and then I have my constant of integration, and then I can figure out what y is by dividing everything by e to the 2x. So therefore y is all of this divided by e to the 2x. And there are other ways this can be written. If you didn't want to write this as an actual fraction, you could bring up the e to the 2x, and it would look like this. So it becomes e to the negative 2x, and then in parentheses I would have the numerator. So I'd have the 1/2 x squared plus the cosine of x plus c. And there you go. So not only did we solve this differential equation, but we were able to get it in the explicit form where quite easily we have our y isolated and we have it as a function of x. Now it's a general solution because I didn't give you an initial condition, so we still have our plus c, but this is our solution to this differential equation, right? So now let's see how this process relates to our linear differential equations, right? So just recall the standard form. So the standard form of a first order linear DE is, so that's where you have the dy dx plus y times, or let me put the p of x in front. So you have your p of x times y, and then you have some other function over here which we will call q of x, right? So the whole goal of this process is the left-hand side here, we can see the two terms. We can see one term that has the dy dx and the other term that has a y. But it's not necessarily in the form where we could just say that it is like do our product rule in reverse and write this as the derivative of some product. So it might not be in that particular form, but the trick is, could we find a special function that when we multiply the differential equation by that function, it puts it in that form. So I can recognize and do my little trick of reversing the product rule and then solving for y like we did in this example, right? So the key to getting the differential equation in that form is a function that we call the integrating factor of the differential equation, right? So define this special function. So this is a formula, and it's a very important formula. So define the function mu as e to the integral of this function p of x dx, right? So this mu, in fact, let me put a little box around it. This is an important formula, right? And it's called the integrating factor of the dE. Now, why is this so helpful? Well, let's take a look at a couple of its properties. Let's say I had to differentiate mu, right? So d mu dx sounds funny. So if we had to differentiate this, well, think about what the rule is for differentiating your exponential function. You'll get back your exponential function, and no matter what's in the exponent, you bring it down. So we'll get back this. But then the chain rule says I have to multiply by the derivative of what's in the exponent. So I'd have to take the derivative of that antiderivative. Well, so I would get my e to the integral of p of x dx back. So that's there. And then think of what happens if you differentiate an antiderivative. Well, you're just going to get back p of x. So you're going to get this back, p of x. So when you differentiate the integrating factor, you get back the integrating factor times the special, well, not the special function, but just the function p. I mean, it might be special, right? But this is your mu, and you get back, or now it's multiplied by my p, right? So that's one important property of this integrating factor. The other one is, let's say we now took the derivative of the integrating factor times our unknown function y, right? And again, both of these are dependent on x, right? Mu is a function of x, clearly, because we have this p of x here. And then we know y is our dependent variable, and it is also dependent on x. So since this is a product, I have to use my product rule. So when I apply my product rule to this, I'll have the derivative of mu with respect to x times y, and then plus, I would have the mu times dy dx. But I just found what d mu is, right? The derivative of mu is mu times p of x. So let's write that in the line below. So this is equal to mu times p of x times y, and then plus mu times dy dx. Now if you look closely, I have a mu in common. So if I factor out the mu, and let me write the dy dx first, and then let me write the p of x times y. So look at what I have in parentheses. I factored out the mu, so then I'm left with p of x times y. This, and I'll scroll back up, that is the left-hand side of my differential equation, right? There it is, the dy dx plus p of x times y. So it seems like what is missing is the integrating factor. In other words, if I multiply the left-hand side of my linear differential equation by mu, I can turn it into the derivative of a certain product, which is exactly what I want, right? So this is the magic function that we need to multiply our differential equation, both sides of the differential equation. This will allow me to do my product rule in reverse and combine the two terms on the left into the derivative of a single product. And that will give me the procedure for isolating y, right? So it looks like a big alphabet soup right now, but once we go through an example, you'll see what the process is. All right. So let's do an example, and then as we go through the example, I'll write down the steps that we need to take in order to solve. Right. In fact, we'll do a few examples here. So the first one, let's say we have dy dx plus 3 times y is equal to 10, right? So what I've chosen here, I've chosen both p and q to be constants. And this is the simplest type, right? Where both p and q are constants. All right. So let's write this down. So our p of x here is a constant 3. And then once we have this, let's figure out what our integrating factor is. So mu is defined as e to the integral of this function, right? So 3 dx. Now, because it's a constant, then those are the easiest functions to integrate, and we're going to end up with e to the 3x. Now, at this step, even though this is an antiderivative, we're only looking for one special function that has the property that we need. So we don't include our constant of integration at this point, right? So in fact, let me make a little note, right? Only one integrating factor, right, is needed. So what does that mean? We take our constant of integration at this step to be equal to 0. So take our c to be equal to 0. All right? It just simplifies. You could certainly carry the plus c throughout the entire thing, and then you're going to get another plus c at the end because there are two integrals that you'll have to end up doing here. And those two constants can actually be combined into one constant. So for simplicity, we just take basically the base function, if you will, or I guess you could say the parent function, and then this will be our integrating factor. Right? So this is step 1, find mu. Right? And it's based on the first order differential equation being in that standard form where the leading coefficient is 1, and I identify my p, and whatever p is, the integrating factor is defined as e to the integral of that function, and then we simplify as much as we can, right? Step 2, now I'm going to multiply the entire differential equation, both sides of the equation, by my integrating factor. So step 2, multiply both sides of the dE by mu, right? So it's going to be e to the 3x times this sum right here, dy dx plus 3y. And then if I multiply the left-hand side, I have to multiply the right-hand side. So then I'll have 10 e to the 3x. And this is where now we're going to look out to see if we can find that hidden product rule pattern. So it's like a treasure hunt, right? And we're looking for that product rule. So let me go ahead and distribute the e. So I'll have e to the 3x, and then dy dx plus 3 e to the 3x times y. And then on this side, I still have my 10 e to the 3x. So if I look closely, I think I see it. I think I see it because I can have this as my f prime, and then this as my f, and then it means that this is my g, and then all of this is my g prime. And there it is. I can see the product rule pattern now on the left. So instead of keeping it as two separate terms, let's reverse it and write down the derivative of the product that we've identified, right? So essentially what we're doing here, we're not differentiating. We've recognized that this is the form of a product rule, and I'm writing down what that product is. So it is the derivative of f times g, or g times f, whichever way you want to write it, because the product is commutative, right? So I can write it as e to the 3x times my unknown function y, right? So the idea is this. So let me just write this. We're not doing a particular process. The only thing we're doing is recognizing the product rule in reverse, right? So we recognize the product rule in reverse, right? So these two are telling me the same thing. So I haven't done anything to change the right-hand side. That comes down as well. So it looks like that, all right? So now that we've combined these two terms into one term, but yes, that term does involve a derivative. If I want to isolate y, then I'm going to have to find an antiderivative of both sides. So integrating both sides, I would get rid of the derivative, but then I'd have to find the antiderivative on this side. So we have e to the 3x times y is equal to the antiderivative of 10 e to the 3x dx, right? And then so let's evaluate this, and this is where we'll need our plus c in order to get our general solution. So we'll have e to the 3x times y. This antiderivative is 10/3 e to the 3x plus c. And then I get to divide both sides by e to the 3x, and then I would have solved for my dependent variable, and I'll get it in this nice explicit form. So y is equal to 10/3 e to the 3x plus c all over e to the 3x. And then just doing a little bit of algebra, I can write this as, in fact, let me show the steps here. So since there are two terms in the numerator, I have to divide both of those terms by e to the 3x. So it looks like this, and then like this. So now I can reduce this fraction. It just ends up being the constant 10/3. And then this one, I can use my property of exponents, and I can write that as c times e to the negative 3x. And there is my general solution. Right? Again, it's general because I don't have an initial condition, but it's an explicit solution because I have isolated my unknown. Well, now it's known. I know what my function is, and we have our dependent variable expressed as a function of the independent variable. Right? So it's, again, a very efficient way of solving. The issue is just making sure that we recognize that product rule in that second step, right? Let's do another example, and in this case, let's make it an initial value problem. So let's say it is 2 dy dx minus x times y, and that is, oh, actually, let's do this. Make it 1 over x And then on this side I have x squared plus 1. Alright, so there's our differential equation, and let's take an initial condition. Let's say that when x is equal to 1, y is equal to 2. Alright, let's see if we can solve this. Well, this one technically is not in the standard form because I don't have a leading coefficient of 1. So the first thing I would do to get it in that standard form, I'd have to divide all the terms by 2. So I'd have to divide this by 2, this by 2, this by 2, that by 2. Alright, so let's see what we have. So we have dy dx. Now, dividing negative 1 over x, so what I'm going to do is essentially divide the coefficient by 2, bring down that minus sign, and we end up with 1 over 2x times y, and then on this side I have 1/2 x squared plus 1/2. So now we can say that this is in standard form, and I can identify my p as negative 1 over 2x, right? So now both my p and q are not constants, but it's still linear, right, in that standard form. So I can identify my p of x as negative 1 over 2x. That means my integrating factor is going to be e to the integral of this, right? So this is e to the integral of negative 1 over 2x dx, right? Well, again, this is not a constant, so we have to integrate this a little more carefully. Now what we can do is we can take out the negative 1/2, so put that in front of the integral, and then I have the 1 over x inside, and then for that one we end up with e to the negative 1/2. Now the antiderivative of 1 over x, that's our natural log of x, right? And we know that there is a relationship between e and the ln, but before I can do that, I have to apply a property of logs. And this is the property that we can use. If you have something multiplying a log of some quantity, you can bring that p up and make it an exponent. So this is equal to the log of a raised to the p power. So I can actually bring up this negative 1/2 and make it an exponent of my x. And then I'll be able to simplify. I cannot simplify before doing that. So it looks like this. Negative 1/2. So now the e and the ln will cancel out, and here's my integrating factor. It's x to the negative 1/2, which in fact, let me leave it like this. Right, we could write it in terms of the roots, but what I'm going to do now is take this integrating factor and multiply the entire differential equation, right? So we're going to do this. Take our x to the negative 1/2 and multiply dy dx minus 1 over 2x times y, and then I have to multiply on this side as well. So x to the negative 1/2 times 1/2 x squared plus 1/2. And then let's distribute this. So we have our x to the negative 1/2 dy dx. And then here I have, so I'm going to write it like this. I have a negative 1/2, and then I have x to the negative 1/2 divided by x. That gives me x to the negative 3/2, and then that's y. And on this side, let's distribute the x to the negative 1/2. So I'll have 1/2. When I multiply the x's, I add the exponents. So that gives me x to the 3 halves, and then plus 1 half x to the negative 1 half. All right. Now here's the thing, and this is the key. We have to look for that product rule so I can identify the f and the g. And I think we can see it quite clearly. If I say that this is my f, look, its derivative is right there, right? This, including the negative 1 half, that is f prime. And then if I say this is my g, then there is g prime, right? So then the left-hand side is the derivative of the product of f times g, right? So we don't even bring down the negative 1 half, because that negative 1 half is what I get by differentiating this in my product rule. So it's the derivative of f times g. So f is this, and then g is that. And then I bring down my expression that's on the right. Right? And this is the really key step, because what it allows me to do is essentially to combine all the terms that has either a y or a dy dx into one term, and then via integration I can isolate, integration and algebra, I can isolate my y. So we have to integrate both sides, so we're going to do that. So then x to the negative 1 half times y is equal to, now when I integrate this, in fact let me write my antiderivative here. So we have x to the negative 1 half dx. Now on this side, this is where I'm going to convert it over to the root or radical notation. So this is y over the square root of x, right? And then on this side, let's see, so when we add 1, we will get 5 halves, and then we have to divide by 5 halves, which is the same as multiplying by 2 fifths. So I will get 1/5 x to the 5 halves. And again, power rule, add 1. This gives me 1 half. And then divide by 1 half, which is the same as multiplying by 2. So I end up with 1 x to the 1 half there, and then I have my plus c. Right? Now, even though we have not isolated y, right, I have my, this would be my implicit general solution. I can go ahead and solve for c. Remember, we had said that the initial condition, in fact, let's go all the way back up and see what the initial condition is. When x is equal to 1, y is equal to 2. So let's use that information to figure out what my constant is. Right? So let's write that down. When x is equal to 1, y is equal to 2. So plug 2 in for y, and 1 in for all the x's. So that's 1. And then that's 1/5. And that's 1. And then that's c. So now I can isolate my c. So let's write this with a common denominator of 5. So this is 10/5. And then this is 6/5 plus c. So c has to be 4/5. So therefore c is 4/5. All right, now remember, we don't circle the c. This is not our answer. Our answer is the function y as a function of x. So I'm going to plug my 4/5 back in. So we have y over root x is equal to 1/5, x to the 5 halves, plus x to the 1 half, plus 4/5. Now, since I want to isolate y, I have to multiply everything by x to the square root of x, or x to the 1 half. So I'll have y equals, so this will be 1/5. So I'm going to write this back with the fractional exponent so that I can simplify these terms. So I'll have x to the 1/2 times x to the 5/2 plus x to the 1/2 times x to the 1/2 plus 4/5 times x to the 1/2. So multiplying all three terms on the right hand side by x to the 1/2, this is what I get. Y is equal to 1/5. Add those exponents, I get a 3, so that's 1/5 x cubed. Add these exponents, and I get x to the first power, so plus x. And then I have this other term here now with my 4/5. And then if you want to go back and write it as the square root of x, that works. And this is our unique solution, guaranteed by that existence and uniqueness theorem. So we found our particular solution that satisfies our IVP, and we're guaranteed that this is the only one, right? So it's a pretty straightforward process. What can become a little bit more tedious is, whatever integration method you might have to use. Sometimes the algebra gets a little bit messy with properties of logs and properties of exponents. But these are things that you're well experienced with, and now you get to use them in the context of these first order linear differential equations. See you in the next video.